In this video, we're going to talk about nth roots and how they relate to rational exponents, and then how to work with rational exponents. Okay, so these two things, the nth root, so the square root, the cube root, those type of roots, they're very closely connected to rational exponents. So let's start with the roots to get comfortable, remind ourselves how those work. So we say that this is the nth root of a. Okay, so notice that the n is on the outside there. When we do a square root, so I'm just going to write here. So if we had the square root of a with a 2 there, we normally just omit the 2. Okay, so if you see one without a number, that's the square root. Oh, that's actually right below. So maybe I'll just erase that. So the nth root of a is equal to b if b to the power n is equal to a. Okay, so to see an example of that, the cube root of 8 we say is 2, since 2 to the power 3 is equal to 8. Okay, so see how that works there? So you want, when you're looking for, say, a cube root, you want to know what number cubed is equal to the number on the inside. Okay, so that's how they work. So some comments. If n is 2, so that's what I said before, we normally don't write the 2, so we would just write square root of a like that without the 2. For any even n, okay, so 2, 4, 6, 8, etc., the nth root of a exists, so it's a real number only if a is not negative. Okay, so it's non-negative. So you can't, so for instance, when n is 2, we know that there's no a, so that when you square it, you get -1. Right? Because when you square something, you always get a positive number. Okay, so a squared is always at least 0. So that means that you can never take a square root of a negative number. So it's the same with the 4th powers, the 6th powers, all the even powers. Another comment, the solution to the equation x squared equals 4, so we're going to talk about this later, but the solution is actually x is equal to plus or minus 2, because 2 squared is equal to 4, and -2 squared is also equal to 4. So we get 2 answers, but the square root of 4 is always just the positive version. Okay, so it's just plus 2. If you want the -1, it's going to have a negative out front. Okay, so yeah, there's a little bit of difference there. So some properties for these radicals, we call them radicals, the roots. So if you have things multiplied inside of a root, you can do the roots separately and multiply them after. Same if they're divided. Okay, so if there are things divided in the root, you can do them separately and divide the results. It doesn't matter what order you do it. So if you have the nth root of some number to the power m, you could actually take the nth root first and then the power of m. Now here's a little maybe confusing thing. So if n is odd, the nth root of a to the n is just a. Okay, that makes sense. The nth root cancels the power n. But you need to be careful if n is even. This is actually the absolute value of a, right? So here, well, there's going to be an example, so we'll go through that. So let's just go through these examples. So if I wanted to know the cube root of 16, well, I know that 16 is 8 times 2. Okay, so this is going to be the cube root of 8 times the cube root of 2. Okay, this is, since 16 is 2 times 8. So because there's multiplying inside, I can do them separately. The reason why I'd want to do that is that we know the cube root of 8 is 2. So this is going to be 2 times the cube root of 2, which is slightly more simpler. If I want the square root of 4 over 9, I can write this as the square root of 4 over the square root of 9. And I know both of these numbers. So that's going to be 2 over 3. So the cube root of 8 squared, okay, 8 squared is 64. I might not know the cube root of that. So I could just switch the order, and I could do the cube root of 8 all squared. So then I know the cube root of 8 is 2. So 2 squared is 4. Okay, and it turns out that 4 is the cube root of 64. Okay, now if I want the cube root of negative 1 cubed, because the power is 3, this is just going to be negative 1. Okay, now for here, I would do this, I can do the square inside. Now I wouldn't want to switch the order here because the square root of negative 1 doesn't exist. Okay, so if I do the square first, negative 1 squared is equal to positive 1. And I know that the square root of 1 is 1. Okay, now this is equal to the absolute value of negative 1. Okay, so because of the even power on the inside, the negative bit is going to go away. So we will get an answer here, but it's going to be the absolute value of what we inputted. An important property that's same with the sum of squares that doesn't have a formula. We also have the same thing for radicals. Okay, so if you have a radical of a plus or minus b, okay, it doesn't actually matter. You cannot break it up. So this is not equal to the square root of a plus or minus the square root of b. Okay, so this is another definitely not. Okay, now to show you an example, okay, I don't know the square root of 4 plus 9. Okay, this is equal to the square root of 13. Okay, it's not a nice number. If I try to break it up, I know these two. So this says it's 5. Okay, but these guys are not equal. Okay, 5 is definitely not the square root of 13. So that shows that when I broke it up like that, that actually did not work. Okay, so that's a bad thing. So when we want to simplify, we want to use these rules to break down our root. Okay, so I'm going to do part A and leave part B for you. So I have the cube root of negative 16x to the 4. So I'm going to break this down. I'm just going to split all the bits up. So this is the cube root of everything that's multiplied. Okay, so I'm going to be, in fact, I can take out the negative 1 if I want, or you can leave it with the 16 or whatever, it doesn't matter. Okay, x to the 4. So I can break them all up like this. Cube root of negative 1 I know is negative 1. Okay, now 16, we already did this one, but it's 8 times 2. So we know that this is the cube root of 8 times the cube root of 2. Similarly, x to the 4 is x cubed times x to the power 1. So I can also break this one up. So it's going to be the cube root of x cubed times the cube root of x. So negative 1, cube root of 8 is 2. Cube root of 2 is stuck there. Now cube root of x cubed, because the powers is odd, I know that that's equal to x. And then I have cube root of x here. So if I put all these things without roots out front, I'm going to have negative 2x. Okay, and then I can actually go backwards as well. So because this one and this one are multiplied, I can actually put them back under the same cube root. So it's going to be negative 2x times the cube root of 2x. Okay, so that's my simplified version. So you give a whirl to part B here. Another way we can simplify, so I'm going to skip part C and do part D instead to be different. So I want to simplify. So I'm going to break everything down like we just did. So I have 3x times square root of 9 times square root of y plus 4 times square root of 25 times square root of y. The reason I'm breaking it down is because the numbers inside are actually nice squares. So this is 3x times 3 times root y plus 4 times 5 times root y. So 3x times 3, that's 9x. Oops, I missed the root y. So times root y plus 20 times root y. And then if I want, I could factor out the root y, and it would be 9x plus 20. Okay, so I can simplify so that I don't have any nice squares inside my square root. Okay, another thing we do often when we have expressions with roots is rationalize the denominator. Okay, so this will be important if you're going on to calculus. Sometimes they even rationalize the numerator. But what it means to rationalize the denominator is that you write a new rational expression so that the denominator has no radicals. Okay, so there's no roots in the denominator. And the main tool that we're going to use is the difference of squares. Okay, so most of the ones we're going to do are just have square roots. Okay, so the difference of squares, just to remind you, x squared minus y squared is x plus y times x minus y. So the idea is if we have one of these and one of them has a square root in it, I can multiply by the missing piece so that it's two things squared. Okay, so that's the idea. I'm going to do A and C again. So for the A, I'm actually not going to use the difference of squares. Okay, for part B is where I'm going to use that. So here, I want the denominator so that it doesn't have a root. So what I want to do is multiply by a fancy 1. Okay, now I want to multiply by a fancy 1 so that I don't have a square root on the bottom. So what do I need to multiply root 3 by in order to not have a root? Well, one thing I could do is root 3, because then it's root 3 squared, which is just 3. So if I do that on the bottom, I have to also do it on the top. Okay, so this is going to be 2 root 3 over, and then on the bottom it's root 3 squared. So it's just going to be 2 root 3 over 3. And now I don't have any radicals on the bottom. So there will still be some, likely, but they're just not in the denominator. Okay, now let's try part C. So here is where I want to use the difference of squares. Okay, so again, I want to multiply by a fancy 1. So what I'm going to do is I'm going to let this part be my x and this part be my y. So in the difference of squares, I sort of have this bit. Okay, so what I want to do is multiply by this bit. So that's the same two pieces, but with the opposite sign in between. Okay, so it's going to be 2 root 3 plus 3. And whatever I do to the bottom, I have to also do to the top. Okay, now I'm going to actually expand this out so that you see what happens. Okay, so let's do the denominator first. So I have to FOIL it out, right? So it's these things multiplied together. So it's 2 root 3 times 2 root 3 plus 2 root 3 times 3, the outer ones, plus the inner ones. So that's negative 3 times 2 root 3, and then plus the last ones, negative 3 times 3. Okay, I guess I can do the top as well. So this is going to be root 3 times 2 root 3. Again, I am using FOIL, so those are the first ones. The outer ones, root 3 times 3. The inner ones is minus 1 times 2 root 3. And the last ones is minus 1 times 3. Okay, so now we just want to simplify. So when we look at this term, we just want to multiply these 3 bits together. Okay, so it's 2 times root 3 squared. So that's actually going to be, maybe I'll write that. So this is 2 times root 3 squared, root 3 twice. So that's going to be 2 times 3, which is 6. Okay, and then I'm going to have 3 root 3. And then I'm going to have a minus 2 root 3, and then a minus 3. Okay, now on the bottom, so here I have 4 things to multiply together. So if I put the numbers together, that's 4. And then I have a root 3 squared. So this actually turns into a number. Okay, it's going to be 12. And then I have plus 6 root 3. And then I have minus 6 root 3. And then I have minus 9. And we can see that these things cancel out. And that's always going to happen when you're using, so this thing that I multiplied by, this is called the conjugate. Okay, so it has the same 2 pieces, okay, but the opposite sign in between them. Okay, we call that the conjugate. So now if I simplify this, 6 minus 3 is 3, and then 3 root 3 minus 2 root 3 is just plus root 3. And it's going to be over 12 minus 9 is 3. So I'm just going to leave it like that. Okay, so and notice that, maybe I'll do this in blue. So on the bottom, we ended up getting 2 root 3 squared minus 3 squared. Right? That's what we started with. This was like our x, and this was like our y. So we get x squared minus y squared. So when I square this, this is 4 times root 3 squared, which is 3, minus 9. That's what we got on the bottom. So you don't actually have to multiply it out if you just know it's going to follow this pattern. Okay, this is why we want to use the conjugate, because if I multiply 2 factors of this form, I'm going to get the difference of their squares. Okay, so that's the idea. Here's 2 for you to try. So I'm going to leave those for you. And now let's talk about how these radicals relate to exponents, because they do. So a to the power 1 over n is the same as the nth root of a. Similarly, a to the power m over n is equal to the nth root of a to the m, which we know is the same as the nth root of a all to the m. Okay, so that's how they relate. Now, if we try to solve some of these, so here's the properties. I think these are actually similar. So these are just exponent rules. Okay, the exponent rules apply to these radicals. Excuse me. So if you have something to a power, you want to multiply the exponents. If you have multiplication with the same base, you want to add the exponents. Okay, so this is power to a power. Okay, then you multiply. This is multiply with the same base. Okay, then you want to add. Division with the same base, I'm going to stop writing those. Division with the same base, you want to subtract the top one minus the bottom one. If you have 2 things that are multiplied together to the power n, then you can bring the power through. Let's just again remind ourselves that if we have them added to the power n, then it can definitely not come through. Okay, only for multiplying and dividing can it do that. And finally, if you have a negative exponent, it's the same as 1 over the thing to the positive exponent. Okay, so let's use these to simplify these examples. So 4 to the power 2, all to the power 1 over 4. This is going to be 4 to the power 2 times 1 over 4. So that's 4 to the power 1/2. So that's the square root of 4. So that's going to be 2. Okay, similarly, x squared times x to the 1/3 is x to the 2 plus 1/3. So that's x. I'm going to have to make a common denominator here. So 2 is the same as 6 over 3. So this is going to be x to the 7 over 3, which we could write as the cube root of x to the 7. Now, maybe I should say when I tutor sometimes high school students, these things I've heard. My favorite one I think is hats and boots. Okay, so the top one is your hat. The bottom one are your boots. Okay, boots are outside the door. Okay, and the hat is on your head. Okay, so I think this is a funny way to sort of remember where the exponents go. But you don't have to use that. I just think it's funny. Okay, next example, 2 to the power 3 divided by 2. So this 2 on the bottom is like to the power 1. So because I have the same base, this is actually 2 to the 3 minus 1, or 2 squared, which is going to be 4. Okay, 2x all to the power 4. This is 2 to the power 4 times x to the power 4. And 2 to the power 4 is 16. So that's going to be 16x to the power 4. 2 to the negative 3 is 1 over 2 to the positive 3. And 2 to the positive 3 is just 8. So this is going to be 1 over 8. Okay, a couple more examples. And again, to be different, I'm going to do B and D and leave A and C for you. So for B, I have a negative exponent. I don't like the negative exponent, so I'm going to immediately drop it down. So this is 1 over 8 over 27 to the positive 2/3. So then if I rewrite this, this is 1 over, so it's the cube root of 8 over 27, all squared. Which I can break up that cube root, so it's the cube root of 8 over the cube root of 27, all squared. And I know the cube root of 8 is 2, and the cube root of 27 is 3, so all squared. So that's going to be 4 over 9 when I square both pieces. And then here's important to remember that this is my big line. So I do, and we could actually change the 1 to be 1 over 1. So it's a fraction over a fraction. So this is 1 over 1 times 9 over 4. So you flip the bottom one and multiply. So my final reduced version is just 9 over 4. Okay, let's try one with x's. So part D. I'm going to just make a note here. So I have x plus 1 to the 1/3 plus x times 1/3 times x plus 1 to the power negative 2/3. Now this is like what they're going to look like if you go ahead into calculus, like Math 108. You will be simplifying things exactly like this. Okay, so we do want to know how to do it. Now I'm going to use there's sort of two ways you can do this. I'm going to use, what one should I use? Okay, I'm going to do one of them, and then we'll talk about another one and go over it in class, I think. So if you look at these, I have two terms, okay? This term and this term. And they actually have something in common, right? I can see that there's x plus 1 in both. But the exponents are weird, okay? So when we did the pulling out the common factors, we always had integer exponents and positive integer exponents. But it doesn't actually matter. So what we can do is we can pull out x plus 1, and you always just take the smaller power. Okay, so here that's the negative 1. Okay, now in the first term, I'm going to have some x plus 1s left. Okay, I'm not actually sure what that's going to be. And then in the remainder, the other term, I just have 1/3 times x. Okay, so I want to think about this exponent. What is it going to be? So when this comes in, I have the same base, so I'm going to be adding the exponents. Okay, so let's just, I'm just going to write on it, but so let's call this y. So if this is y, I actually need negative 2/3, so I'm going to be adding my exponents, and I need that to equal my old exponent. Okay, so whatever the new exponent is, when I add it with negative 2/3, I need to get my old exponent 1/3 because I shouldn't have changed my expression. So to solve for y, I want to add 2/3 to both sides of this equation. So this tells me that y is actually 1, or 3/3. So 1/3 plus 2/3. Okay, so that's actually so this is actually x plus 1 to the negative 2/3 times x plus 1 plus 1/3 x. Now, the negative exponent, I can drop it down to the bottom as a positive exponent. And then here, I have x plus 1/3 x, that's 4/3 x plus 1. So again, I don't, so this is 4/3x plus 1 over the cube root of x plus 1 squared. Now, we don't like complex fractions, so this fraction within fraction thing is not good. So what I could do is multiply both of these, the top and the bottom, by 3. Okay, when I do that, I'm going to have 4x plus 3 over 3 times the cube root of x plus 1 squared. Okay, so that's one way that you can factor out this x plus 1 to the lower power. That's actually not the method that I usually do. So another method that you could do, and it's a good idea to practice this and see which one you like better. I don't have room to put both here, but we can talk about this in class. You could immediately, in this one expression, deal with the negative exponent first. Okay, so that's going to drop it to the bottom. And then you can make a fraction here, and then make a common denominator and put them together that way. Okay, that's actually the method I prefer, but a lot of people prefer this factoring out method. I always just find that coming up with this exponent can be challenging, although it's often 1 when you're dealing with derivatives anyway. So that is working with radicals and rational exponents and how they're related to each other. I highly recommend that you do some practice in this because these are things that tend to cause problems for students.